Hey, today's topic is related rates. Let's start with an example. We all know that the area of a circle is a function of its radius. In particular, the area is pi times the radius squared. Now imagine that the radius of a circle is changing as a function of time. Well, if that's the case, then the area is also changing as a function of time, but it's not changing completely independently as some, unrelated function of time. The way the area changes over time is related to the way the radius changes over time by this equation here that relates the area of a circle to its radius. Let's get very specific. Here is a typical example of a related rates problem. It says, suppose the radius of a circle is increasing at a constant rate of 3 feet per second. How fast is the area increasing when the radius is 100 feet? And let's see if we can't dissect what this problem is telling us and asking us. And if we look at the end, the question, how fast is the area increasing? That's asking us to find the rate of change of the area, or in calculus terms, find dA dt. In other words, the answer to this question will be the answer to what is dA dt given all these other conditions. And what are the other conditions? Well, one of them is that the radius is 100 feet. And the other is that the radius of the circle is increasing at a constant rate of 3 feet per second. Or in calculus terms, dr dt, the rate of change of the radius, is equal to 3 feet per second. All that's left is to put this information together so that we can find dA dt, and the key to that is this equation right here that relates the area to the radius. If we start with that equation, area is equal to pi r squared, we can then take the derivative of both sides with respect to the one variable in this situation, which is time. Area and radius are both changing with respect to the variable time. And so this is an implicit differentiation problem, except it's not in the same sense that we are used to, where one of the two variables that we're looking at, either the a or the r, is the variable in this case. The variable is time, and both of these two things are functions of the variable time. On the left, the derivative of a with respect to t, or the derivative of the area with respect to time, is just dA dt. On the right, it's more complicated. Pi is just a number. R is not the variable, it's a function, and we've got r squared. So this is a chain rule problem. We have to treat the r as if it were the variable. And if r were the variable, the derivative would be 2 pi r, or r to the first. And then we have to finish the chain rule by multiplying by the derivative of the function we just treated like a variable. And the derivative of r is dr dt. And now we're in great shape to plug in the things we know and try to compute the thing that we're looking for. We know that r is 100. We know that dr dt is equal to 3. And after you plug those numbers in and do a little simplifying, you get that dA dt is equal to 600 pi. We're not quite completely done. This is supposed to be this is supposed to answer the question of how the area is changing over time. And just a number on its own, 600 pi, doesn't answer that. It's changing as 600 pi square feet per second. So these related rates problems will always have units associated with them in the answer. So the answer here, 600 pi square feet per second. As the radius is increasing, so is the area increasing, and this tells us how. Okay, you try this one. Suppose the area of a circle is increasing at a constant rate of 50 square feet per minute. How fast is the radius increasing when the radius is 100 feet? So take a couple of minutes, determine what it is you're looking for, determine what it is you know, see if you can't do this problem. It's very similar to the one we just did. Pause the video, and when you're all done, start it back up again, and we'll finish it together. Just like in the previous problem, you have to start with the area equals pi r squared and take the derivative of both sides with respect to the variable t, and you get that dA dt is 2 pi r times dr dt. The problem asks, how fast is the radius increasing? That's find dr dt. And we're trying to find dr dt when the radius is 100 feet. And the other information that we're given is that dA dt, the rate of change of the area, is 50 square feet per minute. That's how fast the area of the circle is increasing. And so plugging those values in gives us this equation right here. And after you simplify, you get that dr dt is 1 over 4 pi feet per minute. If the area is measured in square feet and the rate of change of the area is in square feet per minute, then the rate of change of the radius is in feet per minute. Okay, let's change the problem slightly, except that this time we'll ask how fast is the radius increasing when the area is 16 pi square feet. So take a minute or two if you need it, and pause the video and see if you can compute the answer to this question, and then start it back up and we'll see how you did. You once again have to start with the area is pi r squared, take the derivative of both sides with respect to time to get that dA dt is 2 pi r dr dt, where the derivative on the right comes from applying the chain rule. Based on what the problem says, we are trying to find dr dt when the area A is equal to 16 pi square feet, and we're given that dA dt is 50 square feet per minute. And so we can plug in our value for dA dt, it's equal to 50, but the problem is we don't have a value for r. In order to find dr dt, we need to know what r is, and the problem doesn't tell us what r is. On the other hand, the problem does tell us what the area is, and there's a famous equation that relates the area to the radius. So that since we know that the area is 16 pi, we ought to be able to figure out the radius. By plugging in 16 pi into this formula, we get 16 pi equals pi r squared. And when you simplify and do a little bit of algebra, you get that r is either positive or negative 4. But r is the radius of a circle, and so it's not going to be negative 4. That doesn't make sense as a distance. And so we get that r is equal to 4. We're now ready to finish the problem. We can plug in r equals 4 and solve for dr dt. And after you do a little simplifying, you get that dr dt is 25 over 4 pi feet per minute. The units are in feet because we're talking about how the radius is changing, and the radius is measured in feet. And the problem has already told us to measure time in minutes, so it's feet per minute. Let's do another example. This one is a classic. We've got a 25-foot ladder leaning against the side of a house, and the question is, if the base of the ladder is pulled away from the wall at a constant rate of 2 feet per second, then how fast is the top of the ladder moving when it's 15 feet above the ground? It helps to draw a picture. Here we have shaded on the left our house, and then at an angle that's the ladder, and then the line along the horizontal line is the ground. We're given the length of the ladder, it's 25 feet. And since we're going to have to do some math on this, we may as well come up with variables or names for the other sides of the triangle. I like B for base and H for height of the triangle. We're told that the bottom of the ladder is moving away from the house at a constant rate of 2 feet per second. That means that this value of B is increasing at that rate. In other words, the problem tells us that dB dt, the rate of change of the base, is 2 feet per second. The rest of the problem asks us, how fast is the top of the ladder moving? That means how fast is the height changing? In other words, find dH dt at the particular moment when the height is 15 feet. And it should make sense to you that as the base changes, so does the height. They are related in some way, but what we have not yet come across is what is their precise mathematical relation? What is the relation between these values that we have here, B, H, and 25? And the answer is that by the Pythagorean theorem, h squared plus b squared is equal to 25 squared because we have a right triangle here. And now we're in great shape. We can take that formula that we got from the Pythagorean theorem and take the derivative of both sides with respect to the variable t. Well, on the left, the derivative of h squared with respect to t is a chain rule problem. H is a function of t. So you treat the h as if it were a variable, and then you have to multiply by the derivative of this function that we just treated like a variable. And that gives us 2h times dh dt. Same thing, b is a function of time, and so to take the derivative of b squared, you need the chain rule, and by the same logic, you get 2b times db dt. On the right, you have to be a little bit careful. 25 squared is not a function of time, or I guess if it's a function of time, it's a constant function of time, and the derivative of a constant is 0. We can now plug in the things we know. We know that h is 15. We know that dB dt is equal to 2. And if we simplify just a little bit, we get that 30 times dh dt is equal to negative 4 times b. But the problem is we need to find dh dt, and we can't do that until we know what b is equal to. So the question becomes, how do we figure out what b is equal to? And the answer is we have this Pythagorean theorem that tells us that h squared plus b squared is equal to 25 squared. And so since we know h, we ought to be able to figure out b. And you could just muscle your way through the arithmetic for this computation. I'm lazy and I don't like to, so I look at this and I see that there's a 5 in the 25 and a 5 in the 15, and so there's a 5 squared in 25 squared and a 5 squared in 15 squared. And if you look at it that way, you can pull the 5 squared out, and what you're left with is 5 squared times 5 squared minus 3 squared, which is 25 minus 9, which is 16, which is 4 squared. And so you end up with that b squared is 5 squared times 4 squared, and you end up getting b is equal to 20. And if you didn't see it that way, okay, go off and square 25, square 15, subtract, take the square root, subtract, you'll get 400, and so the square root is 20. In any case, however you figure it out, b is equal to 20, and we can now plug that in to the computation that we were doing. And after you simplify, you get that dh dt is negative 8/3 feet per second. And you say to yourself, Self, I wonder what that negative is all about. You should feel good about that negative, because that's telling us that the change in height is negative, meaning the height is decreasing, which is just what you would expect. As the bottom of the ladder is pulled away from the wall, the top of the ladder is moving down the wall. So the negative 8/3 tells us that the ladder is going down the wall at 8/3 feet per second. Okay, we'll look at one more example before I turn you loose on your homework, and so try this one. We have a spherical balloon that's being inflated at a rate of 5 cubic feet per minute, and the question is, how fast is the radius increasing when the volume is 9/2 pi cubic feet? And before you pause the video, I should remind you of the formula for the volume of a sphere, and it's just this. The volume is 4/3 pi times the radius cubed. All right, take a few minutes, pause the video, figure this one out, and when you're ready, start it back up again. The first thing we need to do is figure out what the problem is asking us and what is it telling us. It's asking us how fast the radius is increasing. That's the question. Find dr dt, the rate of change of the radius. It's asking us to find that when the volume is 9/2 pi cubic feet, so we know that V, or volume, is 9/2 pi cubic feet, and it's telling us that this balloon is being inflated at a rate of 5 cubic feet per minute. That's telling us how the volume is changing, and so that's telling us that dV dt is 5 cubic feet per minute. And as far as the calculus goes, we start with our formula for the volume, 4/3 pi r cubed, and we take the derivative of both sides of that equation with respect to the variable t. On the left, we just get dV dt. On the right, it's more complicated. r is a function of time, we have to use the chain rule. You treat the function as if it were a variable. And then you have to multiply by the derivative of that function we just treated like a variable, and the derivative of r is dr dt. This simplifies some, in particular the 3's cancel, leaving us with this expression here. And we can plug in 5 for dv dt because we know that dv dt is equal to 5, but we still need to know what r is, or r squared in this case, in order to compute dr dt, which is our goal. And we're not given what r is, we're only given what v is. And so we have to figure out r given v. And that's not too hard to do. We use the formula that volume is 4/3 pi r cubed, and plug in 9/2 pi for the volume. Simplifying, this gives us that 27/8 is equal to r cubed. And you can see how carefully the numbers were chosen. That's a perfect cube, and r is equal to 3/2. We can now plug that back into the work that we were doing before to compute dr dt. And after you simplify, you get that dr dt is 5/9 pi feet per minute. Okay, that's what related rates are all about. There is, of course, a homework with a bunch of problems to try, so do that. Don't forget to have fun, and I look forward to seeing you in class.